Hello student. Dear student, now you will see today here in this online class of Physics for 10. Topic is the activity force acting on a current carrying conductor. Dear student, when the current carrying conductor is placed in a magnetic field, now here the force which are act on the conductor due to the magnetic field. Okay. Here the magnetic force, here the mechanical force which is exerted by the current carrying conductor when it is placed in magnetic field. When it is placed in a strong field magnet or the magnetic field. And here the force which is greater or the maximum when the conductor is placed perpendicular to the direction of magnetic field, and the no force experienced by the current carrying conductor when it is parallel to the magnetic field. Okay, parallel to the direction of magnetic field. Now here you will see the activity by which you can show the magnetic field. Here the force acting on the current carrying conductor due to the magnetic field or when it is placed in a strong field magnet. Okay, let us consider a thick copper wire. What we will consider? A thick copper wire AB, and which one end, upper end, which is connected to the battery or a cell, and the other and the lower end which is leave the free. Okay, and here the second end of this conductor or the circuit which is connected with the mercury liquid, mercury vessel or the vessel which is filled with the mercury liquid, because mercury is a good conductor of electricity. Okay, to complete this circuit, and when the circuit is closed, okay, because when the upper end and which is connected with the battery, positive terminal of the battery, and the lower end of the battery which is connected with the vessel and in which filled the mercury liquid, and when the wire which is hanged, okay, and freely, but when the lower end of this wire which is immersed in a liquid of the mercury, because here the mercury liquid is the good conductor of electricity. On pressing key means when the key is closed, and now the current flows through the wire. Now the current begin to flow in the thick copper wire, and the copper wire begin to move in forward direction. And now the position of the B which contact the B dash, and when the position is at the B dash, now leave the contact of the mercury liquid. And when they leave the contact of mercury liquid, it means no current flows through them, because circuit is break. When the circuit is break, no current flows through them. And when the no current flows through them, now it come back in its original position. Again it press the contact, again it the contact of mercury liquid. Now again it begin to move, and this process is repeat again and again. So here the conductor and which the lower end which touches the mercury liquid, because the mercury liquid which is the good conductor of electricity. But when it leave the contact of mercury liquid, now it placed at that place and where the no flows current, because circuit is break. Now you will see here this activity just like here a U-shaped magnet. U-shaped magnet means here a strong field magnet. Okay, U-shaped magnet. U-shaped magnet. U-shaped magnet or a strong field magnet. Strong field magnet. This is the U-shaped magnet or the strong field magnet having the pole N and S. This is the N and this is the S. Okay, and here the mercury vessel liquid. Here this is the mercury vessel, and it is filled with the mercury liquid. Mercury liquid. and here the wire, and which upper terminal, upper part is connected with the positive terminal, and the lower part is connected here the mercury vessels. Dear student, now you will see that this is the positive terminal, negative terminal. This is the U-shaped magnet or the strong field magnet, and the wire. This is a thick copper wire, and this is AB, thick copper wire, and which upper part? And upper part here you can see that connected with the positive terminal, and the lower part which is connected with the negative terminal, and here the lower part you can see that connected with the vessels, and it is filled with the vessel and which are filled with the mercury liquid. Mercury is a good conductor of electricity. To complete this circuit, and when on pressing key, now the current flows through this wire. Okay, when the current flows through this wire, and then it begin to move, in forward direction. Then it begin to move in forward direction. Here the mechanical force acting on this wire due to the strong field magnet. So we can say that the force experienced by current carrying conductor due to the magnetic field, and the maximum force experienced are acting on the conductor due to when the conductor is placed perpendicular to the direction of magnetic field, and the minimum are the no force experienced by current carrying conductor when it is parallel to the magnetic field. And so, and the direction of force which is experienced by current carrying conductor we can find by the Fleming left hand rule. You know that I told you Fleming left hand rule, and when we stretch our three finger of left hand in such way they are mutually perpendicular to each other. Now the first forefinger is pointed in the direction of magnetic field, and the central finger which is the direction of induced current or the current, and then here the thumb point is give the direction of force or the direction of motion of conductor. So here the direction of force we can find with the help of Fleming left hand rule. Okay, and here when the current flowing through the conductor, and now here the conductor begin to move in forward direction, and here you can see that when it reach at the position of B dash, and now leave the contact of mercury liquid, and when they leave the contact it means circuit is broken, and when the circuit is break and no current flows through this wire, and when the no current flows through this wire, now it not going forward, it come in backward, it's their original position. Once again when it come at original position, now it touches the mercury liquid, and once again here the current flows through the wire, now it begin to move. This process repeat again and again. This is the activity by which we can observe that force experienced by current carrying conductor due to the magnetic field, because here the conductor is placed in between a strong field magnet, and due to strong field magnet here the force is experienced by this current carrying conductor. Okay, and the force are here the mechanical force which is exerted on the current carrying conductor due to the strong field magnet or due to the magnetic effect of current. Dear student, when we change the direction of current, now change the direction of here the magnetic field, or when we change the direction of our polarity of this magnetic field, now reverse the direction of current. So here when we change the direction of force of current carrying conductor placed in magnetic field can be reversed by the direction of current flowing in the conductor. So here the direction of force which can be changed on reversing the direction of current. Just like here, I told you in right hand thumb rule. I told you in right hand thumb rule, and when we change the direction of current, now the direction of magnetic field which will be reversed. And here in this case, when we change the direction of current, now change the direction of force which is experienced by this current carrying conductor. So the direction of current carrying here the direction of force we can find with the help of Fleming left hand rule, not by the Fleming right hand rule. By Fleming right hand rule we can find the direction of induced current. Direction of induced current. Dear student, here we can write the force experienced by this current carrying conductor when it is placed between the strong field magnet, and here the circuit is completed by the mercury liquid which are filled in this vessel. Because here upper part here this is connected to this positive terminal, lower part it is connected with the mercury filled liquid, because when pressing key, this is key, when the key is pressing, this is key, this is battery, this is the wire, thick copper wire, and when the pressing key, now here the wire begin to move in forward direction, and when we leave this position, now break the circuit, no current flows, and then here it come back in their original position. Once again when it come back in their original position, and now it touches the mercury liquid. Now once again here the current flows through them, and then it begin to move, because here the force experience, which is the force which are acting on this wire due to the magnetic field, now it begin to move. And so the conductor begin to move due to the force acting on this conductor, and the force experienced by the current carrying conductor due to the magnetic field. Okay, I told you here this force which is directly proportional to what? Strength of magnetic field. I told you in the previous video, and it is also directly proportional to the induced current or the current which are flows in this wire. And here this is directly proportional to the length of conductor also. By this equation, we get here the F is equal to B I L. Okay. Here we can use the proportionality constant, and if we use the proportionality constant K is 1, and then we get here, because we can write here first of all F is equal to constant K B I L. If K is equal to 1, then F is equal to B I L. From this equation we can find the force. If we had given in the numerical problem strength of magnetic field, induced current, and the length of conductor, then we can find the force experienced by current carrying conductor. From this equation we can find the unit of magnetic field also. D is equal to F upon I into L. Here this is Newton upon, and here meter. So here the unit of magnetic field is what? This is Newton per ampere meter or Tesla. What is this? Tesla. Tesla is the SI unit of magnetic field, or Weber per meter square is also the unit of magnetic field. So we can find the unit of also, and the direction we can find with the Fleming left hand rule. By the Fleming left hand rule, I told you, when we stretch our three finger of the left hand such that they are mutually perpendicular to each other, just like here you can see that this is here. You can see here this is the 90 degree, this is 90 degree. In such way, they are mutually, these fingers are mutually perpendicular to each other. So when we stretch our three finger of left hand, in such way they are mutually perpendicular to each other, and then the first forefinger, this is the first forefinger, which is pointed in the direction of magnetic field, and the central finger is pointed in the direction of current, and then our thumb which gives the direction of force or the direction of motion of conductor. So we can find the direction of force with the help of what? By the Fleming left hand rule. And here there are two cases when the wire is placed perpendicular to the direction of magnetic field. Now the maximum force experienced by current carrying conductor. Okay. First case is here when the conductor or current carrying conductor placed perpendicular to the direction of magnetic field, and then the force experienced maximum. Now the maximum force experienced, maximum force acting on the conductor are experienced, and when it is placed perpendicular, no force experience no force experience, no force experience when it is placed, when it is placed parallel with the direction of magnetic field. Direction of magnetic field. Direction of magnetic field. Okay? There are the two cases. When the current carrying conductor is placed perpendicular to the direction of magnetic field, now the maximum force is acting on the conductor or experienced by the conductor. And when the current carrying conductor is placed parallel to the magnetic field, no force acting or the no force experienced. And there are also two cases, because F is equal to, just like when the angle of inclination is theta, now the magnitude of force experienced by current carrying conductor. If their angle of inclination is theta, now the magnitude of the force experienced by current carrying conductor F is equal to BIL sin theta. This is very important question. F is equal to BIL sin theta. From this equation, if theta is equal to 90 degree, it means perpendicular. Now F is equal to what? BL. Okay, if theta is equal to 0, now F is equal to 0. Why? Because sin 90, which is 1, and sin 0 is 0. Okay? Sin 90 is 1 and sin 0, 0. This is the, you will get in trigonometry. This is the trigonometric ratio. So here you can see that if the inclination angle between current carrying conductor and magnetic field is perpendicular or 90, and the maximum force experienced by current carrying conductor. And if the inclination angle between them is 0, now it is parallel. Current carrying conductor and the direction of magnetic field both are parallel, and then there is now no force experience. Okay.